Okay, and hello everybody again, and it is my very great pleasure to introduce the third lecturer, Elisabeth Werner. And Elisabeth, I'm not sure that you were here when I opened this meeting, so if you okay, but I just wanted to thank you again for being a lecturer. Okay, so please.
Thank you. Thanks very much, Dima, for organizing this. Of course, we all would have loved to be in St. Petersburg in person, but these days one has to do the best that we can, and I'm sure you are doing a wonderful job. And I want to thank everybody also coming so late, because for some people it's really late in the evening. So yeah, thank you. So I'm going to, so the first part of my talk will be about not so much randomness, but about some things that we will later see are appearing naturally when we'll be talking about random polytopes in the second part. So the first part will be about floating bodies, and affine surface area. And also feel free always to ask me questions if you have questions. Okay, so I'll start with floating bodies. And there are actually several notions of floating bodies. I'll start with the first one, which was looked at historically as actually the first notion of floating body. And that goes back to Dupin in the 17th century even. And then it was taken up later by Blaschke. But only by Dupin and Blaschke, well, Dupin mostly in dimension 3, but by Blaschke and Dupin only in dimension 2 or 3, and for bodies that are sufficiently smooth. And they defined for a convex body K. Now let's already go to the situation where we look at convex bodies, not just only in dimension 2 and 3, but in dimension n. So K will always be for us a convex body in Rn. So just to be sure that we are on the same plane with everybody. So K, a convex body, what is that? Is a compact subset of Rn with non-empty interior. So such that the interior of K is different from the empty set. So this is a convex body. And how did Dupin and Blaschke define for a convex body the corresponding floating body? Well, we'll give ourselves also a parameter delta, a real number that's positive. And then according to Dupin, the Dupin floating body and I write it like so, K sub delta in these brackets is what? So is the set that has boundary given by the centroids, the center of gravity, the barycenter of what? Of a hyperplane. Now Sakar already introduced what a hyperplane is, so I don't have to do that. Of a hyperplane H that cuts off a set of volume delta, a set of volume delta of K. So let's see a picture. Sorry about that. let's see a picture. This is always this problem. So we'll have a convex body K here in Rn. We look at a hyperplane H. This hyperplane cuts off a set of volume delta of the body K. And what do we look at? We look at the center of gravity, which I have indicated here with the red dot. So this is the center of gravity of, the red dot is the center of gravity, or centroid of H into K. And we look at all such hyperplanes that cut off delta, take the center of gravity, and then we'll trace out the curve or surface that we get by given to us by these centers of gravity, and that is the Dupin floating body. Okay, so that is a definition, and let's look at this definition a bit more closely. But before I do that, let's remark, so note the name floating body comes, of course, from the Archimedean principle. If we have a body that's floating in water, then regardless how you rotate the body around, there is always a set of equal volume above the water surface. That's where the name floating body comes from. Now let's look at let's look more closely at this definition. So let's take an example. So let's look at triangle in the plane, and let's try to compute this object that is given to us by Dupin. Let's compute this Dupin floating body, or let's look what the boundary of this Dupin floating body looks like. So what do we have to do in order to get that? Well, we'll take a hyperplane H that cuts off delta. So up here, now we have volume delta. And we'll take the center of gravity of this H intersected with our triangle. Then we move the hyperplane up here and down there, always doing it in such a way that the corresponding hyperplane cuts off delta, and we'll take the center of gravity. Well, in this case, it's just a line, center of gravity of the line intersected with the triangle. And then in fact, what happens is that we move on a curve that looks like so. So as the hyperplane keeps moving, our center of gravity, we will be moving along this curve like so. But then something weird happens. So let me draw the picture and then explain what is the something weird. So the something weird that happened is that if we trace out these centers of gravity, we'll get actually such an object. So why? Well, we started with this hyperplane here, and then as we move the hyperplane in this direction and down in this direction here, our center of gravity will move along this curve till we hit that point here, which is exactly the center of gravity of the hyperplane intersected with the triangle of the hyperplane that passes through this point here and cuts off delta. So that is the center of gravity of this hyperplane. And then what happens as we keep moving H in this direction and now in that direction, our center of gravity will move along here till we reach this point furthest below on this curve here. And that now red dot corresponds to the hyperplane that is actually parallel to the side. and cuts off delta. So this red dot is the hyperplane that's parallel to this side of the triangle and cuts off delta. And now, again, as the hyperplane keeps moving, we'll march along that curve here till we reach this point, which is the center of gravity of the hyperplane that goes to this upper corner of our triangle and cuts off delta. And then we'll keep going on the rest of the curve. So that is actually the object that we get when we compute this Dupin floating body. We'll get as the boundary of this surface or set, we'll get this object here. So we see that this K delta, the Dupin floating body, need not be convex. And that is a big obstacle for us. We want to stay within the realm of convex bodies, so that is not good for our situation. Right away, this leads to a first question, namely, can we find conditions when this Dupin floating body is convex? So that's the first question, which we will look at in a moment. When is the Dupin floating body okay? So as I said, big problem. The Dupin floating body need not be convex, but we want to stay within the realm of convex bodies. So so to avoid this, we want another definition of floating body, and that's what we are going to look at next. So this is definition. So to avoid this issue of non-convexity, we'll introduce, and that was done independently by Barani and Lahmann. And myself. We introduce what we call the convex floating body. So now let K be a convex body in Rn. And again, we'll give ourselves a positive real number, delta. Then the convex floating body. And I'll put convex in parentheses because from now on, basically, we'll just deal with this convex floating body, and I'll just call it, in what follows, mostly the floating body. So the convex floating body, or just floating body, and I'll denote it by K delta. So is what? So K delta. So K delta is the intersection of all half spaces whose defining hyperplanes cut off a set of volume delta of K. So it's the intersection of all H, say plus here, such that H minus intersected with K has volume delta or smaller. So by volume in its dimension, so here it would be like, as we are in Rn, it would be the n-dimensional volume. So I always denote n-dimensional volume or n-1 dimensional volume. If we are living in n-1 dimension, I denote by these two parallel lines. So what's the picture now? So it's similar as before. We look at hyperplanes H. Those define half spaces H plus and H minus. So H plus and H minus are the two half spaces determined by the hyperplane H. We look at such hyperplanes H so that H minus intersected with K has volume delta or smaller. And we look at all such all such hyperplanes that cut off delta. But then instead of taking the center of gravity, we'll intersect the other, oh, sorry, I want to have it the other way around. That should be H plus, I'll just notice. And here we should have H minus. Here we should have H minus. So we'll take now, so H minus inter K has volume delta or smaller, and we'll take the intersection of all the other half spaces, the H plus. So we'll see immediately that K delta is convex as the arbitrary intersection of convex sets. And what else do we see? We'll see that K0, that is, if we do not cut off anything, coincides with K. And the other thing that we immediately see is that the floating body is always contained in K. Now, there is one more thing that I should say. Of course, delta cannot become too large. It shouldn't be larger than half the volume of K, say, because otherwise you'll just end up with the empty set. So it's understood that the delta is such that we just not end up with the empty set. So maybe a few examples. So let's look at this triangle that we had just now. So we've seen that the Dupin floating body looked like so. So it was this non-convex set. And now what we get if we look at the floating body, so K delta, the floating body, I'll draw in blue. So that's just that object here, and it is of course convex. There is one thing though that this example illustrates right away, namely we see there are points on the boundary of K delta where a support hyperplane I don't need to explain this either because Sakar also explained what is a support hyperplane, what he explained for a polytope. For a general convex body, it's the same. So there are points on the boundary of K delta where a support hyperplane cuts off more than delta. Namely, this hyperplane here that's parallel to the side of the triangle cuts off more than delta, because we'd seen that the hyperplane that goes through that point here, I tried to indicate in red, this has cut off exactly delta, and we have moved further down with this one, so it cuts off more than delta. Okay, now other examples. Obvious example is the Euclidean unit ball. Or I could take a ball with radius r, doesn't make any difference. So Euclidean unit ball, I'll denote like so. So that's the Euclidean ball centered at 0 in dimension n with radius 1. And we can exactly, and as it has all the symmetries, as Euclidean unit ball has all the symmetries we want, the floating body of the Euclidean unit ball will again be a ball. And the only thing that we have to determine is its radius. And it's actually, the radius is actually, we can compute that. It's 1 minus Cn delta to the 2 over n plus 1, so that it is its radius. So we'll get, this is again a ball with this radius, and we know exactly what the constant Cn is. It is, Cn is 1/2 n plus 1 over now the n minus 1 dimensional volume of the n minus 1 dimensional unit ball, and we have to raise that to the power 2 over n plus 1. So we can compute this. And I want to mention one more example where we will see something later, and that is, so one more example, the square in Rn, no, just in the plane for starters with side length 2. And naturally, I wrote it in a way that it's the L infinity unit ball in dimension 2. So actually it is in dimension 2, the L infinity unit ball. So looks like so. So it's the square centered at 0. And here we have 1 and here is 0. Then we can compute here the floating body or the boundary of the floating body. And I write down the function that gives us the boundary of the floating body. So in the first quadrant, otherwise we have to modify with the absolute values and whatnot. So f of x, so this is the boundary of b to infinity delta. In the first quadrant, this is given to us by 1 minus delta over 2, 1 minus x. And I want to mention this for two reasons. The first reason is that we note something here, namely, so we note a property here of the floating body, the boundary of the floating body. So boundary, I'll denote the boundary of a convex body, I'll denote by this D sign here. So the boundary of a floating body need not be C1. That is, need not be continuously once differentiable. How do we see that with this example? Well, if I complete the picture of the floating body in this example here, then it would look like so. And actually, what happens is we have, let's do it in blue, we have a hyperplane H that cuts off a set of volume delta that is a support hyperplane to my floating body here. But it's not only this hyperplane that is supporting the floating body in that point and cuts off delta, we'll also have this hyperplane that cuts off delta and supports the floating body in that point, and likewise this one. So this shows that the boundary of the floating body need not be necessarily convex. So that's the first thing we want to note with this example. The second thing we want to note is that how did we actually compute the shape of the boundary of the floating body in that case? And there I mentioned two facts, which brings us back to the Dupin floating body. And the first fact is as follows. So if the Dupin floating body is convex, then it actually coincides with a convex floating body. So that's the first fact. And the second fact, this is a theorem due to Meyer and Reisner, which says that if K is a symmetric body, and we can assume without loss of generality a zero symmetric body, so what does it mean, zero symmetric? It means x in K is equivalent that minus x is in K. So if K is such a body, then actually the Dupin floating body is convex. That is, the Dupin floating body by the fact 1 coincides with K delta. So this actually, now if we look back at our L infinity unit ball, this actually is a zero symmetric convex body. So we can actually use the Dupin construction to get the shape of the boundary of the floating body, because this Dupin construction is really convenient to, at least in low dimensions, to construct the convex body. So, but this in that example we can do because of these two facts. All right, I want to mention a few more properties. So some more properties. of the floating body. And as I said, we'll basically stay with the convex floating body, and that's the one that I'll be talking about. We have seen that the boundary of the floating body need not necessarily be C1, that is, but it has another nice geometric property, namely the floating body is always strictly convex. And another property I want to mention is that so they are not exactly the same, the Dupin floating body, and most of the time they are not exactly the same, the floating body of Dupin and the convex floating body, but there is still some properties. As I said, this is a nice property to construct the floating body if one knows it coincides with the Dupin floating body via this barycenter property. Of course, the floating body does not always have this barycenter property for every boundary point, but there is still something nice in that direction, namely the following. We have that through every point, I guess what I want to say, they are not the same, but they carry some properties, they have some properties joined. So what's this next property? It's to every point on the boundary of the floating body, there is at least one hyperplane that cuts off a set of volume delta, a set of volume delta of K, and this hyperplane touches the boundary of the floating body in exactly this one point, which is then the center of gravity or the barycenter or the centroid of H inter K, if we call the hyperplane H. So there is still this, there is still something related to the Dupin floating body going on for this convex floating body as well. Now, so that's the floating body or the convex floating body. Now the question is, why do we look at? Why consider floating bodies? And that's our next topic. So that would be 1, 2, which is the affine surface area. I'll start giving the definition of affine surface area, and then we'll go from there and see how the two concepts are related. So again, K is a convex body in Rn. Then the affine surface area, so that's definition of affine surface area now. I'll denote it like so, AS of K. So that's what? It is the integral over the boundary of K. We integrate kappa at a boundary point X, and I'll say in a second. We integrate kappa raised to the power 1 over n plus 1, and we integrate with respect to the usual surface area measure, d mu K. So what is kappa? So kappa, this is the Gauss curvature, or maybe I write it, and I may as well write it. So where kappa is the Gauss curvature, at x in the boundary of K, and mu K is the usual surface area measure on the boundary of K, meaning that if this function kappa were not there, or if I write it, if we look at just the integral over the boundary of K d mu K, then we'll just get the surface area of K. Okay, so before I, okay, so let's say this first. We note that that there is also some issue with this definition, because we see a priori affine surface area is only defined if K is sufficiently smooth so that the Gauss curvature exists. Gauss curvature, for Gauss curvature, we need second derivatives. So a priori, this definition can only be done for convex bodies that are sufficiently smooth. And that's a huge drawback. We want this affine surface area defined for all convex bodies because, as we'll see in a moment, it has many nice properties and it's actually a very useful concept. It's a very useful concept because, in a sense, what it does, it measures the boundary behavior of a convex body. So it comes in naturally in questions of approximation of convex bodies by polytopes. And it has many other nice properties which make it a useful notion to have around. And a useful notion to have around, not just for sufficiently smooth bodies, but really we want it for all convex bodies. Before we elaborate on that further, let me note that sometimes it will be convenient for us to rewrite this integral over the boundary of the convex body as an integral over the sphere. And then I'll write, I'm running out of space. So I write fk, so I'll explain in a second. So this can be written as an integral over the boundary of the sphere of the function fk raised to the power n over n plus 1 u, d sigma of u, where sigma is the usual surface measure on the boundary of the sphere, and where fk, let me squeeze it in here, sorry about that. Or maybe I'll do away with what's below here and write so the fk is the curvature function of the convex body K at U, that is fk of U is 1 over kappa of x, such that the outer normal, which I'll denote like so. So the outer normal of the boundary point x of K is equal to U. So picture, I squeeze the picture here. So we'll have the boundary point x here. The outer normal is, I'll denote by nx, and the curvature function and the Gauss curvature, respectively x and the boundary point and the point u on Sn-1 are related like so. And that will be sometimes convenient to have this integral over the boundary of the sphere instead of the boundary of the body. Okay, so now maybe it's a good point to also look at examples for the affine surface area. Again, maybe I write the definition again, for the moment only the one where we integrate over the boundary of K, the Gauss curvature raised to the power 1 over n plus 1, 16 UK. So that's the definition. And let's look at computing the affine surface area of the Euclidean unit ball. That's as our first example. And then that's easy because what do we have to do? We have to integrate over the boundary of the Euclidean unit ball, that is over Sn-1, the Gauss curvature at a boundary point. At Gauss curvature at a boundary point of the Euclidean unit ball is 1. So we are just integrating over the surface of the Euclidean unit ball with the usual surface area measure. So we'll just get the n-1 dimensional volume of the boundary, which is n times the volume of the Euclidean unit ball. So that's one thing. Now, the other example that I want to look at is polytopes. So let P be a polytope. So if we compute the affine surface area of P, then we see that almost everywhere on the boundary, the Gauss curvature is actually 0. So almost everywhere on the boundary, we integrate the function 0. So we'll see that the affine surface area of a polytope is 0 for every polytope. And that we'll need in a second when we discuss a little bit the properties of the affine surface area. The first property I want to mention is that it is an affine invariant. So what does it mean? It means if T is an affine map with determinants different from 0, then the affine surface area of Tk is the determinant of T, absolute value to the n-1 over n plus 1, the affine surface area of K. So it has this affine invariance property. Now, if we look at the definition up here of the affine surface area, that's not at all obvious from this definition that we have this affine invariance property. But we'll get back to this in a moment and actually see that it's quite natural. The second property I want to mention is that it is a valuation. That was proved by Schütt. So what does it mean? This means that if we look at the affine surface area of two convex bodies K union L, and of course it has to be like so that K union L is again convex. So K, L are convex bodies such that K union L is convex, plus the affine surface area of K intersected L. This is the affine surface area of K plus the affine surface area of L. So it has this nice valuation property. And it is upper semi-continuous. That was shown by Ludwig. So what does it mean? It means that if Kj converges to K in the Hausdorff trick, then the lim sub of the affine surface area of Kj, J, overall J, is smaller or equal than the affine surface area of K. Note that the affine surface area.
And Elisabeth, sorry, before going to the next page, is it okay that for polytopes you ignored the facets of low dimension when you consider on the previous page? Is it okay you consider example for polytopes, and is it okay that you ignored some boundary points, facets
yes,
of low dimension?
Measure 0. You see, you integrate with, this is the measure.
Yeah, I understand, but still on the previous page you said that for this definition the boundary must be C2 everywhere. Did you?
Yeah, I was getting a little bit ahead of myself. It's a priori, you know, a priori, you are absolutely right. A priori, this we have not yet defined, right? So I completely agree with you. I was getting a bit ahead because I wanted to make this point about the approximation continuity. Yeah, you are right.
Okay, I see. Thanks.
Yeah, you are right. As before we said, which is completely true, because a priori affine surface area is only defined if Gauss curvature exists, and of course at the for instance vertices of a polytope it does not exist, but we'll see in a moment that we can define it, and then it's completely consistent that the surface area of a polytope is 0. And what I wanted to, or why did I say that? I wanted to say that because, well, we have the upper semi-continuity property of the affine surface area, but we cannot expect continuity of the affine surface area, so that will be okay, which we'll see in a moment. And this shows us that we cannot expect continuity because we know that every convex body can be approximated in the Hausdorff metric by a sequence of polytopes. And so in particular, also the Euclidean ball can be approximated by a sequence of polytopes. So, so that shows us that affine surface area cannot be continuous for the Hausdorff metric, or in the Hausdorff metric. Because we find PJs that converge to the Euclidean unit ball, and the affine surface area of PJ is equal to 0 for all j, but the affine surface area of the Euclidean unit ball is strictly bigger than 0. So that's why I wanted to mention that right away, to show that we cannot expect continuity, only upper semi-continuity.
Okay.
And now the last property I want to mention, that is the affine isoperimetric inequality. Which says that the affine surface area of K versus the affine surface area of the Euclidean unit ball is smaller or equal than the volume of K divided by the volume of the Euclidean unit ball raised to the power n minus 1 over n plus 1 with equality if and only if K is an ellipsoid. So what it says if you fix volume, if you look at all convex bodies with a given fixed volume, then the affine surface area is maximal for ellipsoids. So in particular for Euclidean unit ball. Right. Now this affine isoperimetric inequality is really extremely useful and provides a solution to many problems where the extremum is an ellipsoid, which again shows us that it would be really useful to have this concept of affine surface area defined for all convex bodies. Before I go to how this can be done, I want to talk a little bit about the affine isoperimetric inequality a little bit more, and then basically I'll do the same thing as I had done before. So I'll assume we already know there is an extension to all convex bodies, and as I had done for polytopes, and talk a little bit about in more detail about this affine isoperimetric inequality and what it is related to. That's okay? So, actually what I want to say is that is the following, namely that this affine isoperimetric inequality So in a sense, I'm getting ahead of myself again and assume that we have it already for all convex bodies, affine isoperimetric inequality, that is this affine surface area and consequently all its properties, including the affine isoperimetric inequality. So this affine isoperimetric inequality is equivalent to the Blaschke-Santalo inequality, which you may know. So what does Blaschke-Santalo inequality say? So in order to talk about Blaschke-Santalo inequality, we need to say what's the polar body of a convex body. So K is a convex body in Rn, then so K convex body in Rn. And we'll assume that 0 is an interior point of K, which we can always do because everything that we will be looking at is invariant under translation. So we can always shift the body so that this happens without changing the setup. So 0 is an interior point of K, then K polar is the set of all Y in Rn such that the inner product Yx is smaller or equal than 1 for all X in K. So like if we have a square, that is the n infinity ball, then the polar is the L1 ball. So d n infinity polar is the L1 ball, which I've drawn here, at least in 2 dimensions. And then the Blaschke-Santalo inequality says that there exists a unique S0 in the interior of K. And in order that I don't have to define, to make things more complicated than they should be made, we assume without loss of generality that S0 is equal to 0. So there exists, that is, if it's not at 0, we'll shift K and it won't change anything. So there exists a unique S0 in the interior of K, which without loss of generality, we can assume that it is equal to 0, such that if we look at the volume product, volume of K times volume of its polar, this is bounded above by the volume of the Euclidean unit ball to the squared. The Euclidean unit ball is of course its own polar. So so we have this with equality if and only if K is an ellipsoid. So this is the Blaschke-Santalo inequality. Do I say that now? Yeah, maybe I'll say this now, and then we'll talk about this equivalence of Blaschke-Santalo inequality and affine isoperimetric inequality in a moment. So, so we see that this volume product of a body and its polar is upper bounded by the volume product of the Euclidean unit ball and its polar. Now, one can ask questions, what about lower bounds for the volume product? So what about lower bounds for the volume product K polar? And that is brings us to the famous Mahler conjecture. The Mahler conjecture, which says that, okay, if we stay within the set of zero symmetric convex bodies, then the lower bound is K polar is lower bounded by, for instance, the volume product of the L infinity unit ball and its polar, which is the L1 unit ball, which we have set up here. So that would be of the order, or would be equal 4 to the n over n factorial. So this is if we are, so for say zero symmetric K, we have this. And in the case, in the general case, then K polar would be lower bounded by the volume product of a simplex and its polar, which is again a simplex. So S simplex. Sorry, I'm squeezing stuff here in the corner. And what do we know about Mahler conjecture? So Mahler conjecture is open in dimension 4 and higher. And in the symmetric case, so the symmetric three-dimensional case has just been solved a few years ago by solved by Irie and Shibata. So upper bound we know, lower bound is Mahler's conjecture, which is wide open in dimension 4 and higher. But now let's get back to our affine isoperimetric inequality. So I said that affine isoperimetric inequality is equivalent to Blaschke-Santalou inequality. And what we can prove without too much having to introduce too much new stuff is that the Blaschke-Santalou inequality was actually equivalent.
Sorry, Elisabeth, and for a non-symmetric case, it is unknown even in three-dimensional case, right?
I believe so, yeah.
Mm-hmm.
Yeah. Also maybe I should say, so that it was proved by Irie and Shibata, this result in the symmetric case, and there were easier proofs given or shorter proofs given by a number of people more recently, subsequently to their proof. But I'm sure I'll forget to name all the names of the people that were involved in the easier proof, so I prefer not to say anybody's name. Okay, so Blaschke-Santalou inequality is equivalent to the affine isoperimetric inequality. And let's show this direction. As I said, if I were to show the other direction, not too hard either, but I would have to introduce more things that that are not relevant for what we will want to do in the future. So I prefer just to look at the direction which we basically get immediately. So how do we see this? That Blaschke-Santalou inequality implies the affine isoperimetric inequality. So let's start with looking at the affine surface area of K, which, and now I want to use this other way that we introduced it, namely as the integral of the over the sphere of this Gauss curvature raised to the power n raised to the power n over n plus 1, and we integrate with respect to the surface measure on the sphere. And I'll do something trivial now. I'll just write fk times hk over hk. So I haven't done anything. I have just multiplied top and bottom with hk. So what is hk? So where hk is the support function. Should I squeeze it? I'll squeeze it below here. So hk is the support function. Of the body k, that is hk of u is defined to be, so for a vector, we can even take unit vector u is the maximum over all u x, say, X is in K. So what does it mean geometrically? Maybe I'll draw a little picture so that we understand what the support function means geometrically. And then we'll continue our computations up there. So here we have convex body K. Again, we assume without loss of generality that 0 is in the interior, and we look at a vector U. Then what is HK of U? Well, it's this maximum Ux, X is in K, and actually this maximum by continuity property and compactness will actually be attained at a point X0, namely at this point X0 here, such that the hyperplane that touches the body K at X0 with orthonormal U is a support hyperplane so that the support hyperplane, in X0 actually has orthonormal U. So that's the picture. So geometrically, what HK of U is, because we've taken a unit vector U, it's the distance of this support hyperplane to the body with orthonormal U to 0. So that's what geometrically the HK of U is. Okay, so now let's get back to our integral up here. So we want to get back to this integral here, so this expression here. So what we'll do next, we apply Hölder inequality to this. So apply Hölder. And this gives us that this is smaller or equal than the integral over Sn minus 1. And I apply Hölder to take as the one function in Hölder inequality Fk times Hk, so Fk times Hk d sigma. So that is in Hölder inequality, I have taken P equals what? I have taken P equals n plus 1 over n. So I have to take this, sorry. Let's give me some more space here. So we Sn minus 1, so we'll have to take, as this is P, I have to take 1 over P, which is n over n plus 1. And then we'll get as the other integral what's remaining, which is HK. So P is this, which is what we said, 1 over P is n over n plus 1, which means that 1 over Q is 1 over n plus 1. 1 over Q is 1 over n plus 1, which is Q is n plus 1. So we'll actually get HK to the minus n here because the n plus 1 goes away. And we'll have 1 over Q, which is 1 over T sigma, forgot that, 1 over n plus 1. Okay, so far? Sorry, it's getting a bit crowded here, but that's where we are. Now, right, so maybe I rewrite on the next page how far we got. So we got the affine surface area of K is smaller or equal than, so we ended up Fk Hk Sn minus 1, and I'm not writing the d sigma, n over n plus 1, integral Hk to the minus n Sn minus 1 to the 1 over n plus 1. Okay, and why not right away multiply through with the exponent n plus 1? Then I'm having not to carry that all the time either. So it goes away here and it goes away here. And so, so we end up with this. Now I claim two things. So I claim what? So I claim, let me see. I claim that, so claim, which one to start with? Let's start with this one. So I claim that Fk Hk Sn minus 1, this is actually equal to, n times the volume of K. So I claim this. And I claim, so let's write both claims or both things that I claim. And I also claim that the integral as n minus 1 hk to the minus n. This is equal to n times the volume of k polar. So I claim these two things, and I'll show in a second why this claim holds. But now let's assume for the moment we have the claim, then we can write, then we can continue writing up here. Let's move this down. Move this down. Then I can, so let's assume for the moment we have this claim, then we can continue writing up here. So that then also I'll get in the first integral, I'll get n to the n, and I'll get another n here. So in total I get n plus 1, and then I'll get volume of k to the n. And then here I'll get volume, the n I have already taken, I'll get volume of k polar. So I'll get n to the n plus 1. And then I'll keep 1k. So I write volume of, I'll keep one volume of k. I spare one and write only volume of k to the n minus 1. And then I'll have here volume of k polar. Then I apply Blaschke-Santalo inequality, and we'll get that this is smaller or equal than n to the n plus 1, volume of k to the n minus 1. And then apply Blaschke-Santalo inequality, we'll get volume of the Euclidean unit ball to the square. So we have ended up here. Now, we are not quite with our affine isoperimetric inequality, but almost, because now if on the left, where we have the affine surface area raised to the power n plus 1, if we divide by the affine surface area of the Euclidean unit ball, because that's the expressions that after all appear in my affine isoperimetric inequality, we'll get that this is smaller or equal than. Then we would have on the right hand side n plus 1, so nothing happens, k n minus 1. So volume of k to the n minus 1 is good because that's what we want. And then we have this, but then we'll have to divide by the affine surface area of the Euclidean unit ball. But we have seen this is just n times the volume of the Euclidean unit ball. So as it gets raised to the power n plus 1, we'll get to the power n plus 1, and then we'll get the volume of the Euclidean unit ball raised to the power n plus 1. And we'll see this is exactly our affine isoperimetric inequality. So we are done here. And the equality characterizations are, of course, the same as the one that we get from the Blaschke-Santalo inequality. Now, actually, so that shows us that Blaschke-Santalo inequality implies the affine isoperimetric inequality, but the converse is also true. And actually, the nicest proofs that I know for both inequalities independently goes through Steiner symmetrizations. Okay, so the only thing that remains to be seen is the claim. So let's work on the claim. So let's move this away. And let's move this away. And let's look at the claim. Okay, let's do the first part first. So let's look at Fk, Hk, d sigma as n minus 1. Right. So recall when we looked at the affine surface area of K, we basically did write this, or basically, well, I should have said that then, I forgot. So basically what we noticed, or what we used when we were rewriting this, we were using that d mu k, the surface measure of on the boundary of K, can be written as Fk times d sigma. And that's what we want to use. That's what we use when we do the passage from integrating over the boundary of K going to the boundary of the sphere and vice versa. This is the relation that we are using. And I want to use that now, going instead of integrating over the boundary of the sphere, again integrating over the boundary of the body. And then I'll write fk d sigma as d mu k, and recall that hk of u, that was the maximum over all u y or y in k, but the maximum was actually attained at a point x, such that u is the outer normal at x. So I can actually write this as, if we want to take now the viewpoint of a boundary point x, that is, if we want to take the viewpoint of being on the boundary of k instead of looking at u being on the boundary of the sphere, so we can write that as nxx. So that's what we are doing here. This gives us that expression here. And why can we see that that is actually n times the volume of k? Well, that's a nice geometric picture. So picture is as follows. Again, I'll assume that 0 is in the interior of k. And what do we have here? So let's say here is our boundary point x with outer normal nx. And here is the support hyperplane. We've already seen that xnx, this thing here, is hk of u, is the distance, so that is now xnx, is the distance of the support hyperplane in to the boundary of the body in x to the origin. So what is it that we are looking at when we are looking at this expression here? We are looking at d mu k, so we are looking at a little surface element that we multiply with this height. So what we are looking at is we are looking at a cone with base d mu k of x and this height here. That is what we are looking at. Well, so again, what we are looking at here is the volume of such a cone. Well, let's take away, let me write so that we really get a volume of a cone. Let me write 1 over n here and 1 over n here. So then we are, if I put the 1 over n, then we are looking exactly at the volume of such a cone with base d mu k and this height here, the inner product of x and its outer normal. And what we'll do, well, we'll sum all those little cones up, and then we can see that we get the boundary of k. So that is the, we'll get the volume of k. And that is telling us that this first claim holds. Now let's look at the second claim. That is equally easy, or at the second part of the claim, that is also easy. But instead of showing what we have written here, I'll show the equivalent thing being starting out with the volume of k instead of the volume of k polar. So instead of showing, so instead of showing that k polar is 1 over n, maybe I want to bring the 1 over n to the other side, as n minus 1, 1 over hk to the n d sigma. We show volume of k is 1 over n integral Sn minus 1, 1 over hk polar to the n d sigma. So we'll show this instead. And then we'll get, of course, that volume of k polar. So then we'll get volume of k polar. That is 1 over n, the integral Sn minus 1, 1 over hk. That's not quite nicely positioned. So it should be k polar to the n. So we would get k double polar to the n, but hk double polar, that is of course hk by the bipolar theorem. Okay, so so that is also easy. So why does this hold? So k polar, k volume of k, this is just the integral over the characteristic function of k dx over Rn. Then we pass to polar coordinates, so as n minus 1, and then r goes from 0 to infinity, characteristic function of k. So instead of writing x here, I write polar coordinates ru, say, r to the n minus 1 dr d sigma of u. And then we see actually, okay, so we have here characteristic function of k, and we march in direction u. So here is 0, here is our direction u. And we see that, okay, if we look at ru, r going from 0 to infinity, actually characteristic function of k applied to this ru only makes sense as long as we stay inside the body k. So we only actually are allowed, or only make sense, or we'll only get something if we march up to what I will call rk of u times u. And so what is rk of u? So rk of u is called the radial function of k at u, and it's defined to be, so it's equal to the maximum over all lambda bigger or equal than 0. So we want the vector u to be not the 0 vector, such that lambda on u is in k. So this integral here, makes only sense if we look at as n minus 1 integral r goes from 0 to rk of u, and then it is 1, and otherwise, it only makes sense if we go up to here. And so we'll have Rn minus 1 dr d sigma, and that is so what we get. Let me erase here so that I have space to continue writing and I don't have to go to another page.
But Elisabeth, please do not spoil your notes too much, because
okay,
the participants would like.
Yes, okay. Yeah, and I noticed that I'm hurrying because I want to get the argument finished before my time is up, which is soon. So what do we get? So we'll get 1 over n integral as n minus 1, and then we'll get rk of u to the n d sigma. That's not exactly what we want, because what we want is not this rk, but what we want is the support function. But these two are actually related. So I go to, so what I claim now is that we can replace this, or let's write it. What I claim now is that rk of u, this we can replace by 1 over hk polar to the n of u. So I claim that we can replace this by that. And that's not hard to see. How do we convince ourselves of this? Well, one direction is pretty obvious. Which one was easier? Let me see. So, well, they are both easy. So let's. So I want to start now with this one. So let's look at hk polar of u. This, by definition, is the maximum over all u x or y. Y is in k polar, and that is attained at some, which we already said, is attained at some y0 in k polar. But that's again the same as u, and then I rewrite y0, then I rewrite, because what we want to bring in is this quantity here. So I'll bring it in by force. So it's rk of u, rk of u, and that is 1 over rk of u y0 Rk of u. And what do we know? We know that this y0 is in k polar, and we know that this is in k. So we look at an inner product of an element in the body and its polar body, so we know that this is smaller or equal than 1. So we'll get that this is smaller or equal than 1 over Rk of u. That's the one direction, and the other direction is equally easy. So we know that Rk of u, this is in k, is actually in the boundary of k. Okay, so this is our direction u. Here is Rk of u. And so we know there exists y0 in the polar, which we have basically used already up there. And when we looked at the support function, such that what happens, such that 1 is equal to y0, Rk of u. And this is, I'll bring out the Rk of u. We end up with y0 u, and that is of course smaller or equal than Rk of u, smaller or equal than Rk of u. So so Hk of u, because Hk polar of u, because here we have u0 is in k polar, and this is the maximum overall u in k polar. So this is the other direction. So this shows the little claim, and that shows that and that finishes with this little claim, that finishes the proof of that Plaschke-Santalo inequality implies the affine isoperimetric inequality, and as I said, they are really equivalent. So now I see.
May I ask a question about this? And since we have an equality for ellipsoids, and you used Hölder inequality, it means that for ellipsoids, these two integrands must be proportional, right?
Right. Yeah.
And is it obvious?
Oh, it's not obvious. I haven't thought about it, but it must be. And I don't see it immediately. Let's see. Where
Okay. Does it matter? Okay.
So we are talking about here, right? For ellipsoids, yeah, must be.
So it means for ellipsoids, there is a connection between these two functions, some nice connection.
Yeah? Oh yeah. For ellipsoids, there's connection. Exactly, you are absolutely right. For ellipsoids, there's a connection between those two functions, and what's the connection? Yes, you are absolutely right. The connection is, now I'm probably messing up the powers. I'm probably messing up the powers. So.
Yeah, but okay, it doesn't matter.
But
you answered my question. Yeah.
Yes. So support function times thing support function times this to everybody to the right powers is a constant, if and only if k is an ellipsoid.
Okay. Thanks.
Or equivalently, instead of saying this way, you can say, writing the support function like so: power kappa x power. So this is constant, even only k is an ellipsoid. And
yeah, I just didn't know about it, so it's actually very interesting.
I'm not completely sure what's the powers. It's one is, it has to do with n+1 and n-1.
Yeah, but it doesn't matter now. Just I will find somewhere.
It's
later.
a result of Petty, so it's a Petty.
Okay. Thank you.
And yeah, I guess I'll stop here, and then we'll see next time. Tomorrow we'll see how, because a priori we still have the affine surface area only defined now for sufficiently smooth bodies, and we'll see tomorrow how to extend it for all convex bodies. Okay, thank you.
Thank you very much, Elisabeth, for a very interesting talk and other questions. Okay, if you let, I have two questions. First one, as you showed at the beginning, am I right that we have that floating body always is a subset of another floating body? Convex floating body is always a subset of this Frenchman floating body. I forgot the name.
Dupin floating body.
Dupin, yeah, Dupin floating body.
This, well, I have not actually shown it, but it's so that this is, well, in the case of the triangle, it was like so that this.
Yeah, but you gave us some properties that for everybody, for every point of the boundary of the floating body, there exists a hyperplane such that there is intersection has the volume delta, and this point is buried center. Yes.
Mm-hmm.
So it implies that K delta in square brackets always contain K delta, right?
So
right? Am I right?
Well, it's a bit problematic because if you look at this floating Dupin floating body, right? So what do you mean by this set? Do you mean?
Okay. Actually,
do we mean
the
that
boundaries? The boundary of this contains the boundary of this. Is it true?
Okay. If you talk about boundary, yeah,
yes.
That is yeah.
Yeah, but sometimes they coincide. Can you describe the class of the bodies for
this is an interesting
question,
and that is not clear at all. Like the only thing that we really know is this: if K is symmetric, then they coincide. So this is this Meyer and Reisner. Otherwise, it's highly unclear how this Dupin floating body looks like. It can look extremely weird. That is, its boundary can look extremely weird. So yeah.
And the second question, yes, from this theorem, Reisner and Meyer, is it possible to calculate the floating bodies, say for ellipsoids or for LP balls?
Oh, for ellipsoids, this is for ellipsoids we can compute. Basically, yeah, for ellipsoids we can compute, but even for LP bodies, it's
so you have some complicated function for boundary, yes, like for square, but more complicated.
Yes, but more complicated. Yeah, it's not so obvious. But for instance, for even in the plane for LP balls, I mean in the plane for the L infinity ball, I have shown, and basically one can kind of say what's the behavior also for the L infinity ball in higher dimensions, say around when we are close to the boundary, and then the equation is given by product of 1 minus xi, I goes from 1 to n, something of that sort. It's given by something of that sort, depending on what the normalization is. Here I probably took, if I write this, I probably put 0 here, and I took side length 1. So then close to the boundary, it will be described for small, close to the corner, it will be described by such a function. But as we are away, from a vertex, it's much less clear. That's for delta small. And if we look at other LP balls, it's pretty hopeless to compute how, because
Even
you have complicated integrals.
Even on the plane, yes.
Even on the plane, yeah.
Okay, thank you very much. Other questions? Okay, if not, let me thank Elisabeth and Manju and Zahar for very interesting lectures. And okay, see you all tomorrow according to our timetable.